And then hide meeting closing. Hide this too. All right. Well, those guys have been waiting around for a while. But hopefully, all right. So what we did, the guys online, what did we do? Homework 14 is not the final thing, which I changed the name of final to like, don't use this one. So homework 14, and then you can join the group. So you can join with other people, whoever you want to join with. Is that it? You have to spool all the way to the bottom. It takes like half an hour. And then you get to homework 14, and then you can join. You can either make yourself a group or you can join a group with someone else. That's the deal. Up to 4 people. If you want more than that, tell me. Maybe I can do something. All right, so that's that. So the first question on the thing for the homework 14 is about wind power that I went through in class, but it wasn't recorded. Anyway, the BETS limit is in the wind power slides on the webpage on slide 27. That's the derivation of it. It's asking you, like, would that work for this other method, which is a link to this after the homework that's about these ionic wind turbines or wind power generators, which I think one of the main points of it somewhere at the bottom, they list at the bottom of this advantages. The advantage is that it doesn't have a BETS limit. It's like you can get, theoretically, you get 100% or almost 100%. Well, that's the question. It's like, can you get 100% from this thing? I mean, you can't get 100% because if you would have to have no wind leaving it to get 100%. So it has to be something less than 100. Or could it be like 99 or something like that? So anyway, and then there's this thing kind of goes through maybe like the math equations for like how that thing works, and maybe the answers here. I don't know. I mean, I think I'm more looking for like a philosophical answer. Like, no, you can't use BETS limit. It's probably how it should begin. Then like maybe what limits it. Then the second thing is like we talked about hydrogen. So different kind of fuels you can get from electricity. So basically we're going to go to like wind turbines or solar panels someplace in the Sahara Desert. They're going to have to be converted to something. So basically you can run high voltage DC from the Sahara Desert, but you can't run it from the middle of the Atlantic Ocean where most of the wind is, right? So but you can cover the middle of the Atlantic Ocean with gigantic wind turbines and no one's going to complain about it, right? Even it might help the fish grow better or something because they have shade, like a coral reef or something forming out, artificial thing forming. So anyway, but the power that you generate is going to be electricity. You need to somehow get it back to the U.S. or somewhere else, right? So anyway, converting it to hydrogen is the main thing. So you use reverse osmosis to get water, and then you electrolyze the water, and then you make hydrogen and oxygen. You dump the oxygen, or you could ship that too. Then you convert the hydrogen to ammonia. That's like the main route because of question A, like the liquid hydrogen is going to be like going to be 20 K. You can't reach that on a wind turbine. Right, but you can take at room temperature 1 megapascal, which is like 10 atmospheres, with just a kind of a roughing pump type thing, and then you can liquefy ammonia, which is just like propane, and you can put it into a propane tanker and ship it. Right, so you could fill up tanks easily with ammonia. So the question is like, how are all these things different in terms of pressure, like pressure and temperature? So if you want liquid hydrogen at atmospheric pressure, then what temperature? So to do that, you need like a program that like calculates phase behavior. This is a Krios thing, which is a cubic equation phase behavior program. So you can download this, then you have to make it so that you can edit it. And on mine, you go under a thing called tools, and you find like allow editing or something on it. But this one, none of these things seem to do that. Like these aren't even menus. These are just the bars up here. Let's see. I need to make it so I can edit this thing.
Can you just edit the values, or do you need to apply values?
No, you just need to edit the blue ones.
The blue ones should be able to be edited.
No, I'm with a password.
No, you don't need a password.
No, it's not doing anything. Does it do it on yours?
Yeah.
All right. Do you have another menu besides this menu? Like one above that, or did you have to unlock it or anything?
No, it just works. It says, like in the instructions, it says blue values can be edited without a password.
Yeah, but did you change any of them?
No,
try to change one, it won't change. You have to.
Or, well, yeah, change the blue values. It's fine.
Why doesn't it work on mine then? There's something, someplace in here I have to change, I have to say like enable editing, yeah. But it's not this menu, it's like the top menu, like this menu, like open email. This isn't it, right? Usually there's two menus on my computers, like this menu and there's another menu up.
Is it another add-in that's for the spreadsheets that can work?
No, you just have to be able to edit the spreadsheet. You have to, there's someplace the spreadsheet's locked and it has to be unlocked. Excel locked it itself, you know. Let's see. I'll find it, I guess. It's in every version of Excel, it's in a different place, you know. And
When I open it up, it says, has the will enable editing at the top. Usually.
okay, let me quit this whole thing. How about that? And then I'll just start over. Wait, I need to quit Excel. I can't even quit Excel. See, there's a menu that's missing on this thing. It's the PC. I blame society. There. All right. It's here someplace. That's Excel. So where's that file that I just had open? Open this thing. There's no enable editing, right?
You might want to re-download it off the website.
Okay. Well, let me see if I can change this.
I
No.
clicked into the critical props tab at the bottom of the page. I guess it wants you to copy paste those values into the
Yeah, that's right. That's what you need to do. I mean, I can just tell you how to do it. I can do it on my computer if that's. All right, let me just do it here. This isn't the first time I've run into this, so I should know how to fix this problem, but somehow I don't remember. That worked. Oh, but the people at home won't see it. They'll see it as a little. No, I think it's important to do this. I'll show you guys how to do it. I hope we can communicate with everyone. All right, so I already unlocked it. So you have, all right, so you have, all right, so this is that sheet props, right? I already have it set up with hydrogen. So you have to get the critical temperature. So it's going to use like reduced temperature. It's going to be like T by TC. So you need TC, you need PC, and you need this omega, the eccentric factor, which are all like here, like TC, PC, omega for kind of everything. And then hydrogen is right here. So you copy the name hydrogen and the three numbers. And you take those and put them into props. So you put it like right here. Hydrogen and those three numbers, and the blue will turn black because you put in new numbers. Right. And then you need to put in, because so this is going to go from like condition where your hydrogen is, and it's going to go to ideal. So you need a departure function. So you need to go, and then once you get there, it's going to use the ideal heat capacity to go to some other temperature and then come back with a departure function to get to the actual where you are, right? So you need these critical temperatures to get the reduced temperature pressure, and then you need the heat capacity to do the transitions. That's the ideal heat capacity. So it's because you're doing the departure function and the transition and back. So anyway, so the ideal heat capacities are all here, and you don't need the name, you just need the four numbers. So this is like the first number is like the heat capacity, and there's T times the next one, and T squared times the next one, and T cubed times the next one. So it's a Taylor series expansion for heat capacity, right? So you copy that and then put those into props like over here. So it's that 3 steps, right? Two steps. 1 step is opening it, 2 steps of copying those. Then you need a reference state, because so there's actual values of like enthalpy, and it has to go back to some reference state, right? So you need to go to reference state and pick the reference state. So I said 298 in like 1 atmosphere, 0.1 megapascal. And then it's gonna, this is calculating the cubic equation has 3 roots. So you're gonna have like, the top one has a large volume, so that's the gas, large specific volume, and the bottom one has a small specific volume, that's the liquid. So it's like liquid vapor equilibrium, the middle one's never used, right? Those are the 3 roots for the cubic equation. So this is a vapor state, hydrogen at 1 atmosphere and 298, right? And then so number 1, that's your reference state. You wouldn't use the imaginary state for reference state. You wouldn't use the liquid because the liquid doesn't exist. So you have to use, it says in the red, like you have to use one of the red ones. And the other things are like, what do you want to use? So you can either set the enthalpy to 0 for the reference state or the internal energy. So either one's okay. And then 0 for and then the reference state is either, if you use an ideal gas reference state, it doesn't need to do a departure function from the beginning to the end. And if you use real gas, it's going to have to do a departure. So it doesn't matter which number you pick. Just pick one. It's just like how it does the calculation. So I put 0, 0. And this 1 matters. That has to be one that has a real root. So that one's 1 for this case. And the rest of this is just parts of the calculation. Anyway, then you go to props and you want to know, like say you know it's like somewhere near, like say it's 50 Kelvin or something. You know it's cold, right? So you say like 50 Kelvin. All right, so that's like supercritical, right? So it doesn't have any vapor, it doesn't have any liquid, it's just got 1 number. It's a supercritical fluid. It's like too hot. You've gone above supercritical temperature. You know the critical temperature is 33, so 50 is too hot to begin with, right? So, and I have it at atmospheric, so 0.1 megapascal. If you put 1 megapascal, it'll be supercritical the whole time, right? So anyway, so basically you have to find the thing. So the way to do that, like the chemical potential for at the phase separation point, the liquid and the vapor have the same chemical potential. And the fugacity, like KT ln of the fugacity is the chemical potential. So if they have the same fugacity, they have the same chemical potential. Like 2 phases in equilibrium, liquid vapor have the same chemical potential, same fugacity, right? So you have the fugacity of the liquid, fugacity of the vapor. You want the ratio of those to be 1. So this thing is like wherever it gives the equation, which that's not shown, but basically the equation for that is like the ratio of the liquid to the vapor fugacities. So you want that to be 1. So right now we're supercritical, so we have to cool it down. So you go to like say 20, 22 or something. Then you have 2 phases. You have liquid vapor and equilibrium, but it's not at the equilibrium point, right? So you want to know at that pressure, what's the boiling point of hydrogen? So at this point, the fugacity, the lower fugacity wins. So that at this point, it's a vapor. See 0.09 fugacity and then 0.13 for the liquid. So the lower one is the one that wins. So it's a vapor. The lower chemical potential will be the stable state, lower fugacity. So that's a vapor at that point. Right. So she said, like, what's the state of hydrogen at 22 Kelvin and 0.1 megapascal? You'd say it's a vapor. And what's the density of it? Take 1 over that V, that would give you the density of hydrogen at that temperature pressure. Right. So it's got all the information and it just calculates, and it does it for everything, like all single phase. It's just kind of useful. I mean, it's kind of a good little toy. Okay, so you want this thing to be 1, so you have to go in. And then you have to use this solver thing. And you say, I'm going to solve like that thing, like this thing. And I want it to be a value of 1. I'm going to do it by changing this thing, like the temperature. Right. So I want the fugacity ratio to be 1. So I'm at the equilibrium point. The chemical potentials are the same between the 2. I'm going to vary the temperature until I find it. It has to be kind of in range so that you have both vapor and liquid fugacities. Otherwise, this thing's not a number and it'll get lost. Like you can't do it. But if you have values for that, so you have to guess first to get it in range. Then you just say solve, and it just says, do you want that? And you say okay, and it tells you it's 20.42 Kelvin. That's the transition point. So if you want liquid hydrogen, you have to go below that. Like you go like 19 Kelvin or 10 Kelvin. Anyway, go into any of those. You can't do it with helium, which is like 40 or something. So you'd have to have a cryogenic cooler on your windmill, which isn't going to happen. But it's going to be a huge machine, and it probably would take more energy to run the cryogenic cooler than it would be getting out of the hydrogen or from the wind. So the whole thing wouldn't work. So basically, chemical conversion of that hydrogen to ammonia is like the way to go, which is going to be at room temperature. So it'll be 273 Kelvin or 298 Kelvin. And it's going to be it's going to be 1 megapascal instead of 0.1. And then that's liquid ammonia, and that can be shipped around just like gasoline, right? So it's kind of like some simple thing to move around. Anyway, so that's kind of that problem. Anyway, hopefully you can figure that out. Sorry I couldn't get it to work on the PC here. I should have tried it earlier, but I don't know. Anyway, it's because I can't get the other menu to allow me to do the thing. So it says to do that, and then pressure needed to produce liquid. So it's the same thing. Fugacity ratio 1 do it for propane. That'll come out to be 1 megapascal. Room temperature, and ammonia is the same as propane. The point of B and C is to tell you that ammonia is the same as propane. So it seems like ammonia is this odd material, but we found, like I mentioned in a table in class, that ammonia is cheaper than gasoline to burn. So it's kind of like ammonia in current prices, market prices, it's cheaper to burn ammonia than it is gasoline. So it's kind of like, why aren't we burning ammonia? And then just say like that's the better thing to do is convert to ammonia. And that's what people are doing anyway. And then these other things are all from the notes in class, like how to do what the Haber reaction is. But it's good to just go through those before you graduate or whatever. Like those are the main chemical engineering reactions, like how do you make synthetic fertilizer? Those things are like, maybe you should have a rough idea. And there's a bunch of stuff. I don't think it's that hard, the rest of this. It's just like comment on this, comment on that. Could take some time though. But if you make up groups, it'll be faster. But I don't know. Don't worry too much about it. It's basically like Friday, like a week from Friday. A week from tomorrow will be good. If you need more time, you have more time probably. Ask for it. Hopefully like a week from Friday. And then we have everything together. Anyway, so I got a bunch of slides on just like overview of the class, like what we've done in here. Any questions on that Prius thing? So if you have problems with it, email me. I can try to help you with it, like help you go through it. The biggest stumbling block, I think, there's 3 big stumbling blocks. One is just getting it so you have to make it so you can edit the Excel file, because it comes in locked somehow. I'm not sure why. And either you go under the tools menu, and on a Mac, you go under the tools menu, and there's a place that says protection. Click protection and say unprotect or something like that. And on a PC, the way I Googled it, it says to go under file, preferences, and then like there's a place where you say unprotect or access to the file. But this is a PC and that doesn't work. Like if you go under file, there's no protection thing. So I'm not sure why it's like that. Maybe actually you could enable editing. Oh, that's this thing. But anyway, whatever. So basically, if you can't, that's the stone. And the other one is like if you have to pick that number 1, like for your reference state, you have to have a real state. So that's easy to make a mistake. That's why he has it in like red there. So you don't pick the reference state, it won't run. And the third stumbling block is getting the pressure right. Like knowing that 1 bar is 0.1 megapascal. That's a key element. And 1 megapascal is not 1 atmosphere. That's a big stumbling block. Because then you can be like searching, you can Google like what's the boiling point of hydrogen? Oh, it's like 20. And you put it in, and it's like gives you all like not a number. Because you're actually at 10 atmospheres, which is super critical. So it's like those are the 3 stumbling blocks that I could see that you'll run into. But otherwise, it should be. I think that's a pretty useful tool to have. I don't know if there's another program to do that, but that one seemed pretty good to me. I mean, I've used that in research stuff, so it's like pretty handy to have. It's a lot faster than trying to look up in the tables or something. Like you want to know the enthalpy of whatever temperature and pressure. Like that'll just spit it out. And in fact, a lot of the tables are created from that Prius formula. So the tables that you're looking up into are that same program. Anyway, so what do we got? So this is just kind of like a trip down memory lane, I guess, if you've been paying attention, but so this course like morphed over the years. So, and this might be the last year that's offered too. So, like we're trying to put in like circular economy plastics as a substitute for this. So it's not exactly the same thing, but anyway, supposedly there's an appeal for that. Anyway, so oh, by the way, so no one wants to do the whatever tour I had on Friday, right? The recycling. Okay. So I'm just gonna cancel it again. I thought I'd give a last chance to see if anyone wanted to do that, but all right. So anyway, which is a topic of that course, that's gonna replace this course. So kind of is a bad indication and nobody wants to look at it, but anyway. So yeah, hopefully you got a little bit about Africa. In the past, it's been a lot more about Africa and a lot less about kind of chemical engineering stuff, and like a lot less about coal, It's like we ended up doing a lot of coal stuff in here, so it's all right. I mean, it's basically coal is actually pretty big in Africa too. So then, basically the idea is like different technologies where you could targeting mostly energy stuff, but how you could like impact things, technologies that could be used to impact things. So, like Africa. And then like corruption is one issue. And then Human Development Index, that's like the UN measure of, the guy from London mentioned Human Development Index, but anyway, so the UN made up this formula of like what development means, like how many bowling alleys, whatever, but so it's got to do with like education, medicine, bowling alleys, whatever. So some kind of mix. It gives a number so they can rank countries according to who needs money. And then you can see like Africa is the place that has no money. Basically, that's the center of it. So the idea is how do you develop it? Energy is the concept. So we had to talk about Ghana. So that's like kind of here somewhere. I think the big one here is Ghana. Right? That's Togo. Togo, I forget what that country is. Sierra Leone just had an election. It's been in the news. And anyway, so we did have Ghana too. So we kind of went through those different places. Then earning income, like kind of how many people are earning less than $1 a day type thing. So Africa is kind of the center of all those things. And then also, like Africa is the growth area, right? So 2100, then like 13 of the 20 largest cities are going to be in Africa. And they're going to be like 100 million people in one city. Like right now, New York, they're saying in this table is like 20 million, right? So this is like 5 times as many people as New York City in one city, right? And there's going to be a bunch of those mostly in Africa, right? Nigeria, DRC, Tanzania, right? So then some in India, but basically majority in Africa. So if you're looking at like where is the market going to be for everything, it's kind of like basically going to be Africa. Everyone's going to live there. So that's where the money is. This is a map of like world's wealth, and this map of the world population below. So it's kind of like the money is being hoarded in the north, and like the south doesn't have much. Then I went through like basically the layout of a photovoltaic system, and then some stuff about what we've done with things like that, and then and kind of how a PV cell works, like the physics of it more or less, and then how batteries work. Kind of went through that a little bit. And then we had Max came in and talked about batteries, Max Yan. And then comparison, we went through a few different energy storage systems and things. This I'm not sure I talked about this, but this is something Max and I did. We had a project where we made these soil moisture sensors. So it's just showing, and this is in Lesotho. We did it in Ethiopia and also in, like, Lesotho is a country in South Africa, in the middle, surrounded by South Africa. But using these in Lesotho's in a mountain, so it's got basically doing the moisture tests in greenhouses. And then also we did that in fields in Ethiopia. So anyway, then desalinization we talked about, and then we had the guy from the seawater greenhouse come and talk about how that system works. Concentrated solar chimneys. I went through a bunch of things. Swamp coolers, talked a little bit about, and then this evaporative refrigeration system. And then GoSun came to talk about the solar cookers and some other kind of technologies they're developing. So charcoal, talked a little bit about charcoal, and then a bunch of things about, actually I didn't put in the coal stuff. I spent a lot of time on coal. And then this business about making hydrogen, basically, using redox reactions and solar heat. So we went through that kind of business. And we had Mobbing to talk about biogas, biofuels. So I posted his slides online, but the video, like, he used his own computer and the video just shows up in the top corner. So you can't see like his slides. Actually, if you have his slides, you could click through while he's talking because you have the audio. You can kind of see in the little box what the slide is. So if you want to look through that again, it's possible to do it. It's a little awkward. Went through like photocatalysis, titania stuff. I didn't go through the spirulina. I usually do that, like algae. You can use algae to make protein. And then you can make, so you can buy, usually I bring in a bag of spirulina and have you eat it. But one time I did that, and a guy like took a big spoonful of it and choked. So I shouldn't laugh, but it was almost like a medical emergency, you know? So, because it's really fine powder, like powdered sugar, except it's green and isn't sweet. So he inhaled it basically, you know. So there's some danger involved in spirulina, I guess. Mostly it's used in the, you know, you get these fruit drink things in a bottle. I forget what the name of it is. Anyway, you can get a green one, and it's almost all spirulina. You know, so you can eat algae. So bottom line, you mix it with fruit juice, it tastes very good. And you can get something happened there. You can get protein from it. Like they were using it. There's this group in Africa that was using it as a supplement for children, you know, to get protein in West Africa. I don't remember what country it was, but it was like Liberia or something, I think. But anyway, but it hasn't really caught on because it's not. It's in health food stores because it's a protein source, and it's not, you know, it's a vegan and also, but basically there's not many people that are going to eat pond scum. You know, it's like kind of like not exactly, but you can also use it, algae you can use to make diesel fuel, which was tried out to a commercial scale and then failed, you know, so in California. So, I mean, you can do it in your lab or something, but basically some algae will produce oil, some algae will produce protein, some algae will produce hydrogen. So depending on what algae you use, you can make a variety of things with it. Some people have done that. So far, as far as large scale use, it hasn't happened. So I think that's why I didn't really talk about it. But anyway, then also vertical farming, I went through some. We had the people from 80 Acres come out, talk about it. And then I talked about offshore wind, it's like or wind power and stuff. So yeah, so the point is just kind of the point of the course is try to get you some idea of technologies that could be used in development, and also how like chemical engineering could fit in with that stuff, and maybe how you could leverage things, and maybe even what the future is going to be like quickly, in terms of the hydrogen kind of economy things in Europe and in Australia, and electrification in the US, based on kind of solar electricity. And then what the options are, and maybe how you could fit in with that stuff. Maybe show you some things you haven't seen before. That's partly the idea, to just kind of expose you to things. Anyway, hopefully you enjoyed that. We've got something out of it. And that's about it. I guess my 43 slides, so that's it. So any comments or anything? Please. So if you have problems, like email me with the homework. It's a lot of questions, but hopefully it's not too challenging, except the Prius thing and the first thing about the wind. Even that's not that challenging, I don't think. So hopefully it's okay. You can kind of get through it. But anyway, thanks for coming. Thanks. I enjoy teaching this class. So it's nice to see you guys here. But that's it. I guess.
Oh, that's true. I was not. I like that right there.